All right, welcome everyone. In the next couple of videos, we are going to discuss how we can set up a nice algorithm for solving systems of linear equations, such as this one over here, which is a system of three different linear equations in three different variables, x1, x2, and x3. So this example, we actually have solved this pretty carefully in a previous video. So I'm just going to reveal the steps here, not get into the details, and you can check my arithmetic. But we start by setting up the augmented matrix, which I have here, and then we perform a series of elementary row operations. So those operations were replacement, interchanging rows, or rescaling a row. So we can, for example, first do a replacement on row 2, then we can do a replacement on row 3, and essentially what we're doing here is applying like the elimination method to a system of linear equations. And then we do another replacement, and at this point we now have row 3 in a very nice form. So if I rescale row 3, I multiply every entry in row 3 by minus 1/6, then I can see from this last row that whatever solution I have, it's going to require that x sub 3 is going to equal 4. And I would like to have a similar way to read solutions from the other rows. So that's why we continue this process. And now we do some more replacement. We do a replacement on row 2. And if you're following my arithmetic, this just means I'm going to replace row 2 with minus 1 times row 3 plus row 2. And now we've got row 2 just about in the right form. If I do a scaling on row 2, I now can see that, okay, x3 is going to have to equal 4, x2 is going to have to equal 2, and now let's do some work with elementary row operations to get the top row into a nice form. So we do a replacement, we need to do a second replacement, and now we can see that from the top row, x1 is going to have to equal 1, and this gives us a solution to this system of linear equations, namely that x1, x2, and x3 are going to have to equal 1, 2, and 4 respectively. So this is a unique solution to this system, but just recall last time, it is possible for a system to have an infinite number of solutions, and in some cases, we might not have any solutions. So let's see how we can generalize this approach on this slide, solving this system for solving any system of linear equations. So we want to generalize this process. So let's kind of talk about how we can now build an algorithm to solve any general system of linear equations, no matter how large that system might be, how many equations we have, or how many variables we have. And the key to this process is going to be using these elementary row operations on the augmented matrix. And the goal is going to be to put this augmented matrix into a special form, like we saw in the previous slide, from which we can very easily read the solutions from that matrix. And the way that we're going to put the matrix into this form is going to be by applying elementary row operations. So here's examples of a couple of forms of matrices that we've had after performing a series of row operations. And once the matrix is in this form, we can read the solution off pretty quickly. So you might want to ask yourself, look at these matrices and think, well, what properties do these matrices have in common? And why is that useful for us when we're trying to solve a system of linear equations? So for example, a couple of observations that we can make is that in these matrices, each row has a leading entry, and that leading entry is 1 in this case. So you can see in the matrix on the left, we have 3 rows. Each row, the very first entry is a 1. And that is the same over here for the matrix on the right. So that's one observation that I can make. The next is that each time we go up a row, notice that the leading entry is now in a column towards the left. So I go up a row, the leading entry is now towards the left of the leading entry over here. I go up another row, my leading entry is now also moved towards the left. And lastly, what was really convenient with these solutions was that above each of these leading entries are all zeros, and below each of these leading entries is also all zeros. And once we have a matrix in a form like this, again, we can read the solutions pretty quickly from that augmented matrix. So let's summarize some of those key properties that we started to discuss from the previous slide. So we say that a matrix is in row echelon form if it satisfies these three properties. First, all non-zero rows would be above any rows of all zeros. So for example, this matrix over here has 2 rows of all zeros. Those rows should be on the very bottom of the matrix, and any row that contains non-zero entries should be above it. And we can, if the matrix is not already in this form, right, we can interchange rows. That's an elementary row operation in order to line it up in this form. This matrix over here satisfies this first property because it does not have any rows of all zeros. The second property is that each leading entry of a row is in a column to the right of the leading entry of the row above it. So for example, here's the leading entry, that's this black square over here. Each time I go down a row, the leading entry is over towards the right. This has a leading entry over here. I go down a row. It doesn't necessarily have to be immediately to the right, but it has to be somewhere over here to the right. I go down, it's to the right. I go down, it's to the right. I go down, the leading entry is over here to the right of the leading entry above it. The third property is all entries in a column below a leading entry should be 0. So here's a leading entry, all zeros. Here's a leading entry, all zeros, and so on. So below each of these leading entries that here I've indicated with a black square should be all zeros. And so any matrix that satisfies these three properties is in a form that we would call row echelon form. And any matrix can be put into row echelon form by performing a bunch of elementary row operations. So we'll develop that algorithm really quickly. And lastly, if in addition to the previous three properties, we add 2 more, and we have seen why these might be useful when solving linear systems, is that if we also require that each leading entry in a row is 1, and that not only are below each leading entry have zeros, but we also require that if above each of these leading entries, we also have all 0 entries, then the matrix is what is called reduced row echelon form, or what might be called Hermite form. And so over here on the left, we have an example of row echelon form, and then on the right, we have a matrix which is in reduced row echelon form. So now each of these is a 1, and again, we have zeros above each of these leading entries. And we want to develop an algorithm to put any matrix into this reduced row echelon form. And so once we have it in reduced echelon form, or excuse me, row echelon form, then we could use scaling operation to make each of these leading entries a 1, and then we can use replacement to eliminate all of the entries above each of these leading entries. And so we will build this algorithm carefully in the next video, but for now, what I really want you to focus on is recognizing what does it mean for a matrix to be in row echelon form, what does it mean for a matrix to be in reduced row echelon form. And so if you are curious, what does this term echelon mean? So echelon is the French word for the rung of a ladder. So it kind of means like a step in some sense. And this has a derivation, echelon, this word echelon has a derivation from military perspective, and that is an echelon formation is a formation in which the units are arranged diagonally. So you could have an echelon left or an echelon right formation. I am not going to talk to you about military strategy, but more where does this name come from? And you can see over here, this is kind of similar to our goal of putting a matrix into echelon form, where these people are the leading entries, you can think of it. Okay, so in the next video, we are going to talk about how we can build an algorithm to take any matrix and express it equivalently in reduced row echelon form by performing a series of elementary row operations.